let me ask you a question. What is the most rebellious substance in the universe? What is the one material that looks at the laws of physics, the nice, clean rules that everything else follows, and says, no, I don't think I will? You might guess something exotic, some rare element cooked up in the heart of a supernova, some bizarre plasma or some strange quark matter. But no, the answer is sitting in a glass on your kitchen table right now. It's water, plain old water. And I want to tell you something that may disturb you. The more I have studied water, the more unsettled I have become. Because water doesn't just bend the rules a little, it shatters them. It does things that, by every reasonable expectation of chemistry and physics, it simply should not be able to do. And the fact that it does these impossible things is the only reason you and I are here to talk about it. So by the end of today, I want you to understand something that most people never think about. I want you to see that water is the strangest liquid on the planet. That its weirdness is not some minor footnote in a chemistry textbook. It is the very foundation of life itself. And I want you to understand why, when you really dig into the physics, the explanation is beautiful but deeply unsettling. Because it means the universe is balanced on a knife's edge. A knife's edge made of hydrogen bonds. All right, let's start with something you've seen 1,000 times. You drop an ice cube into a glass of water. What happens? It floats. You've seen this since you were a child. It's so ordinary you don't even think about it. You'd never dream of calling it remarkable. But let me tell you, if you showed that to a chemist from another planet, a chemist who had studied every other substance in the universe but had never seen water, that chemist would faint. That chemist would look at you and say, that is impossible. Solids do not float in their own liquid. That violates everything I know about matter. And the alien chemist would be absolutely right to be shocked. Because here is the rule that virtually everything else in the universe follows. When a liquid freezes and becomes a solid, it gets denser. The molecules slow down. They pack together more tightly. The solid form is heavier than the liquid form per unit volume. And so the solid sinks. Think about it. When you melt iron and pour it into a mold and let it cool, the solid iron sinks to the bottom of any remaining liquid iron. When you freeze alcohol, the solid sinks. Mercury, gold, copper, bismuth, nitrogen, oxygen, sulfur, you name it. The solid sinks in the liquid. That's the rule. It's one of the most reliable patterns in all of chemistry and physics. Water says, not me. When water freezes, it expands. It gets about 9% bigger. Think about what that means. 9% is not trivial. It's enough to burst iron pipes. It's enough to crack granite boulders. It's enough to split a sealed glass bottle in your freezer, and I bet some of you have learned that the hard way. All of that destructive power comes from the simple fact that water, unlike almost everything else in the universe, gets bigger when it gets cold enough to solidify. And because ice is less dense than liquid water, it floats. Now, I said that sounds like a small curiosity. Let me show you why it is anything but small. Let me show you what would happen if water behaved like a normal, respectable substance. Imagine a lake in winter, a big, deep lake. The air above it is getting colder and colder. The surface of the lake cools down first, because it's in contact with the cold air. Now, with a normal liquid, the cold surface layer would become denser than the warmer water below, and it would sink. Warmer water from below would rise up to take its place. And that warmer water would cool too, and sink. This is convection, and it would keep going, mixing the lake, cooling the whole body of water gradually and uniformly from top to bottom. Eventually, the entire lake would reach the freezing point. And then what? The first ice crystals would form. Being denser than the liquid, they would sink to the bottom. More ice would form at the surface, and it too would sink. The lake would freeze from the bottom up, layer after layer. Every fish, every plant, every tadpole, every bacterium, every microscopic creature entombed in a solid block of ice, dead. All of them. And in the spring, when the sun came back, the ice at the bottom of the lake would be insulated by the water above it. It would be extraordinarily slow to melt. Some of it might never melt. Year after year, more ice would accumulate at the bottom. The oceans, in their shallower regions, would suffer the same fate. Over geological time, vast quantities of the planet's water would be locked away in permanent ice at the bottom of every body of water. Life in the water would be impossible, and since life began in the water roughly 3.5 billion years ago, well, there would be no life at all. No fish, no amphibians, no dinosaurs, no mammals, no humans. An empty, frozen world. And it gets worse. Think about what that bottom ice does to the planet's heat balance. Ice is white. It reflects sunlight back into space. Normally, dark ocean water absorbs sunlight and warms up. But if the sea started accumulating ice at the bottom, eventually that ice would build up to the surface. Now you've got vast white sheets reflecting sunlight instead of absorbing it. The planet cools further. More ice forms. More reflection. More cooling. It's a runaway feedback loop, what climatologists call the ice albedo feedback. Without the density anomaly of water, the Earth might have tipped into a permanent deep freeze very early in its history. A snowball planet, white and silent and dead. You might say, well, surely the tropics would stay warm. Maybe. But without liquid oceans to moderate the climate, without water's enormous heat capacity acting as a thermal buffer, the temperature swings even near the equator would be savage. And without liquid water to dissolve nutrients and carry them around, the chemistry of life has nothing to work with. No medium, no solvent, no life. So this one anomaly, ice floating, is not just a curiosity. It is arguably the single most important physical property of any substance on Earth, and it comes from water's refusal to obey the rules. But water doesn't stop there with just one act of rebellion. Here's what really happens, and it's so clever it almost seems designed, although I hasten to add that's not a scientific statement. Water gets denser as you cool it, just like any well-behaved liquid, but only down to 4 degrees Celsius. At 4 degrees, water reaches its maximum density. That's the point where it's heaviest. And then something deeply strange happens. You cool it further from 4 degrees down towards 0, and instead of continuing to contract, water starts to expand. It gets lighter. The colder it gets below 4 degrees, the less dense it becomes. You see what this does? The coldest water, the water that is closest to freezing, is lighter than the water below it. So it stays at the surface. It doesn't sink. The warm, dense water at 4 degrees settles to the bottom and stays there. So the lake freezes from the top down, not the bottom up. A layer of ice forms on the surface. And here's the beautiful part. Ice is a terrible conductor of heat. That floating lid of ice acts like a blanket, an insulating cap, protecting the liquid water beneath from the frigid air above. The deep water stays at roughly 4 degrees. The fish survive. The plants survive. Life goes on beneath the ice, calmly waiting for spring. All because water has this one peculiar, rule-breaking property. If you are not amazed by this, I haven't done my job. Now, you might say, all right, that's one weird thing about water. Interesting. But maybe it's just a fluke. Oh, but it's not just one thing. The ice floating business is only the first item on a long list of misbehaviors. Let me go through the charges. Let's talk about boiling. Here's a fact that should bother you more than it probably does. Water boils at 100 degrees Celsius. You know that. Everybody knows that. But do you know how absolutely insane that number is? Water is a small molecule. 1 oxygen atom, 2 hydrogen atoms, H2O. Its molecular weight is only 18. That's tiny. Now, oxygen belongs to a family of elements in the periodic table, a group we call Group 16. The elements below oxygen in this group are sulfur, selenium, and tellurium, and each of them forms a compound with hydrogen, just like water. Sulfur gives you hydrogen sulfide, H2S, the stuff that smells like rotten eggs. Selenium gives you hydrogen selenide, H2Se. Tellurium gives you hydrogen telluride, H2Te. Now here's where the pattern should work. H2S boils at minus 60 degrees Celsius. H2C boils at minus 42 degrees. H2T boils at minus 2 degrees. Do you see the trend? As the molecules get heavier, they boil at higher temperatures.